Jumbo! These are the nuclear fission notes. You'll see nuclear fission on the front side and nuclear reactor on the back side. So nuclear fission, fission means to split. So what we're doing is we're taking a large atom, something lower on the periodic table, and we're splitting it into smaller nuclei. And the question is, how do you do that? Well, what it takes is you've got to take a particle called a neutron and you've got to fire it at a nuclei. And what we do is we use uranium-235 in our examples. And you say, why would we choose a neutron? Well, if we fired protons at a nucleus, they could get through the cloud of electrons, but they'd be repelled by the positive charge in the nucleus. If we fired electrons, they would be repelled by the electrons the outside of the nucleus. So a neutron having no charge makes it somewhat easier for it to make a direct hit on the nucleus of an atom. If it hits and sticks, it can cause a nuclear reaction. That means it can fission the atom. When it fissions, it'll split roughly in half. We don't know exactly what it's going to split into, but typically it's going to split into a couple of smaller elements. But it will also release neutrons and it'll release energy. The neutrons it releases can in turn go on and potentially fission other nuclei. And if you have enough mass and enough of these neutrons hitting, then you have what's called a chain reaction. So it reminds us when the split occurs, we get lots of energy because we're altering the nucleus, which has all this energy bound up in it. We get two extremely radioactive atoms that fly away. They're radioactive because they end up having too many neutrons for their protons. They release neutrons and they produce heat that we can use for different functions. The chain reaction is difficult to produce. The nucleus is incredibly small when we have an atom. So you're taking a tiny thing called a neutron and you're trying to hit it with a small target called the nucleus with that neutron. The neutrons have to be slowed down. The energy. Well, it turns out this is a case where mass is converted directly into energy. And so, if we have a sample uranium that says 0.7% of the mass is directly converted into energy, and you have Einstein's famous equation, E equals mc squared. So if you have the mass that's been converted, and you take the c, which is the speed of light, enormous number, and you square it, even a small mass will give off a lot of energy. This happens to be something called mass defect, that loss of mass, as we form a new nuclei. At the bottom of this page, it compares uranium fission with burning coal. Uranium fission, nuclear reaction. Burning coal, chemical reaction. So, it says if you burn a ton of coal, you could heat a home through the winter. If you fission a ton of uranium, so same mass, different material, you would heat all the homes in 100 large cities. So there's simply a lot more energy to be had from this nuclear reaction than from a chemical combustion reaction. Now we're going to look at a nuclear reactor on the back side. And it talks about some of the difficulties. Well, we start with the radioactive material, then we have a radiation hazard. We're also going to make radioactive materials that we don't really know what to do with after the fact. How do we store them? How do we get rid of them? Some of the technical problems, the neutrons may escape. If you run out of neutrons, the chain reaction will stop. Neutrons may be captured by something, nuclei, and not fission. So they hit, but you don't get the fission that you want. And they may simply bounce off. So we have the fuel rods, control rods, moderators, neutron reflectors, and shielding. Fuel rods, these are rods that are simply made of uranium-235, and robots will lower them into what's like a large swimming pool filled with something we'll see called heavy water. In that swimming pool, we're going to have control rods. Why do we have control rods? Well, we have to control the rate of fission. We don't want to go too quickly or too slowly. So these rods made of boron or cadmium are lowered in robotically. And if the rate of fission is going too rapidly, we would put more rods in to absorb those neutrons to prevent other uranium particles being fissioned. If the reaction goes too slowly, then we would lift out those control rods so that there are fewer to absorb the neutrons. Moderators are designed to slow the water. Something called heavy water. It has a heavier isotope of hydrogen. So instead of hydrogen 1, it's going to have a heavier isotope, bigger mass, things like hydrogen 2. And that simply slows neutrons down, so their speed, if they hit the nuclei, they will stick and cause a fission. Neutron reflectors allow the neutron to bounce off the walls of the spool. So if they go all the way through and don't hit a nuclei, they can bounce off the wall and try again and keep going back and forth until they actually fission a nuclei. And shielding, that's going to be designed to protect against radiation. That's going to be trying to protect the people and the equipment with things like lead and thick layers of concrete. The procedure. Most uranium that's mined is not going to be uranium-235. Most is going to be uranium-238. So only about 0.7% is uranium-235. So you have 1,000 atoms of uranium, only about 7 would be the fuel we want. So we have to enrich it to get a higher percentage of uranium-235. We're going to slow those neutrons. We've talked about the reflector. If the reaction's too successful, we could generate too much energy, too much heat, and possibly melt the fuel. Possibly have a fire, although an explosion is unlikely. We've talked about using the control rods. We've talked about the shielding, keeping the reactor core cool. And the radioactive waste is typically considered the biggest problem. What do you do with this stuff? How do you store it safely? And generally that's a problem that we've created and we're leaving, hopefully, for your generation to solve. Along with nuclear fission, we have something called the atomic bomb. And so that is where you simply want to have an out-of-control nuclear fission reaction, and it's described here. But we won't go into detail on this at this point. Next thing we'll do is show you a diagram of a nuclear reactor and a chain reaction